Brown flying a kite at a height of 10 meters. The wind carries the kite horizontally away from him at a rate of 7 meters per second. We're actually answering two separate questions within this. We're answering how fast the distance between Tom and the kite is changing, and how fast the angle is changing between him and the kite. What's nice is they share the same picture. So here's what's going on. Tom is flying a kite right above him. That is where the kite is. So he only lets out 10 meters of string for his kite. But if you've ever flown a kite before, as the wind blows, you can either hold tight to the string you have let out, or you can just let it unravel, and then as the wind blows it, more string unravels. So that's what's happening. The wind is blowing. Stick with me, I'm a math teacher, not an art teacher. The wind is blowing the kite this way, and so now the kite is over here, and he needs to let out more string to allow for the kite to move. So this is the picture we're dealing with. We had a good discussion in class, a couple of us, of why 70 isn't the constant. Because again, 70 is this moment in time. After the wind has blown, the 70 is actually what changed. The 10 was the original constant of this picture. So we're given that piece of information. We are also given that the kite flies horizontally away from him at this rate. So that is actually a dx dt. Anything horizontal is x. And so those are the constants we know. So for the first question, when it says how fast is the distance between Tom and the kite changing, well, the distance, I want you to notice that says distance, not height. The distance between him and the kite is from here, and this is the change in the distance. So this is actually kind of like the previous problem where you're finding the change in the hypotenuse over the change in time. So let's find that. If we are just dealing with exterior, we're dealing with a right triangle Pythagorean theorem problem. And this is where we ask ourselves what's the constant, and it's actually this y value here. So we can actually put 70 squared here, so that when we derive, this is now a constant driving to 0, and this will be our formula. This is now where we can use the 70 meters, because once we derive, we're saying at the moment in time when the hypotenuse is 70 meters, how is that distance between him and the kite changing, or that hypotenuse changing? We know we can, here we go. We can calculate with Pythagorean theorem what the x is when the hypotenuse is 70, and we are given the dx dt. So see if you can solve the rest of this without the video, but then play to check your answer. Alright, after plugging in and solving for dh dt, that is how fast the kite is traveling away from Tom Brown when he has 70 meters, the instantaneous rate that it's traveling. What about the angle now? So I want us to remember SOHCAHTOA, and actually the fact that we have all three sides, we know all the exterior sides of the triangle, we truly could use all of these. We know their rates, so we truly could use these. I really want to encourage you to use the constant in the problem, and again, we said the constant was this 10 here. So if this is our angle, I'm sorry, I mislabeled our sides before. This is our hypotenuse, and the adjacent side It is really helpful to use the constant. It just makes life a little bit easier. So we want to make sure we're using sides with the adjacent. So I would recommend not using sine. That leaves us with cosine and tangent. So truly, it does not matter which one you use. You will get the same answer as long as you do consistent math. So if you want to use cosine, this would be your setup. Cosine of our angle equals our adjacent side, which is 10, over our hypotenuse, which 70 is the instant. We are going to leave h as it. We will plug in our 70 later if needed, but 70 could change, whereas unless Tom Brown changes his position, that 10 will be a constant. So if you want to use this as your equation, you totally can. Hopefully you're recognizing though, and if we are trying to find how fast the angle between Tom Brown and the kite is changing, that's actually finding the change in the angle compared to time, which means you will have to derive this. This is fine. I mean, you guys can derive 10 over h. You would either have to do the quotient rule or bring h up and do h to the -1 and derive it that way. So again, cosine would work, but actually I'm going to advise us not to use cosine, and I'm going to advise you to use tangent. Here's why. Tangent is the opposite side, so that opposite side I'm just going to keep as x because the square root of 4800 is just one moment in time. It changes, so we want this to work for all x. But then the 10 is the constant here. And now this is a little bit friendlier because we can treat this as this is the same as 1/10 x, and that is just a little bit easier to derive. You don't have to use the quotient rule. You can just use the regular derivative rules. The easier ones, I should say. So now that that's there, I'm going to advise you to pause the video and try solving the rest of this on your own. I am going to pause on my end and put out the work, but you at least know the setup now, and I want to truly see how much you can get without me, but play the video when you're ready to see the rest. Alright, go ahead and check the derivative. First, see if you got the derivative set. I converted my secant to 1 over cosine squared and then multiplied that over to the other side. And then remember cosine, that's where we go back to our SOHCAHTOA. Cosine is the adjacent side of 10 over the hypotenuse of 70. So now when we have it derived, we can plug in the instant we want the rate at, and then we just solve from there. You can leave it as a fraction or 3 decimals, please, but we can say that at the instant the kite is 70 meters from Tom Brown, it is changing by 1/70th radian per second.